Hello, Sarah. Hello, Kay. Hello, Lola.
Hi, Dr. Vin.
Hello, Dr. Klee. Hello, everybody.
Hello,
Hi.
Lina.
Hello, Lina.
Hi, Nina.
Hello, Steven. Hello, Boston. Okay. Thank you for connecting and for your dedication to the class. Thank you for tolerating me and being patient with the homework, which is was objectively heavy, as I noticed. I have very ambitious plans, and I already know that I will not be able to fill them in today, but I'll try my best. So I did send slides from previous years, but I'll try to go straight without even talking.
I just connect.
Yeah, that's good. That's good. So there are 5 goals, and it is probably a larger number than I can carry in the head. So I better write on the board. So on one hand, we need skills practice on photon, but at the same time, since the photon will not accommodate 2 large systems, we need to do it on nodes. So, and basically, everything we practice on photon, I want to duplicate and show how to run it on nodes. And this will slow down all process of demonstrations and checking about 3 times. So if you are not very ambitious, if computational chemistry is not your life goal, you can stay within just practice with something important. But if you really have plans to do productive research, then duplicating processes, everything I'm showing on NERSC is critically important, because even those of you who are practicing CCAST may have noticed that sometimes it is fails to do some jobs. If you didn't, maybe your models are not big enough. And NERSC is not solving all problems on the globe, but it is a little more powerful. Another thing we need for the project. So this stuff on NERSC is optional, but very recommended. And then on your personal computers, you need to do visualization of what's how this EMT software. I will fail to demonstrate it today, just because time is up. But by the next Wednesday, please make sure that I know it was part of the homework and you reported. Some of you did made a screenshot of VMD button on your desktop. But make sure you can open software and open some files there. Next Wednesday we will do it practically, and it will be not possible without it. So it will be critical. So it's really so our main goal that I will do at any rate is to practice invisible surface. And it will be done for the model that we did in the previous lab here, like for titanium dioxide nanowire. And your homework, I'll meditate a little bit and I'll assign it on Friday, but it will include to do UV visible absorption spectra for your other models that you love so much. So this is for sure spectrum, and if time allows, is to do the same absorption spectrum on NERSC as well. The transmission of files between photon and NERSC will be, I wouldn't say impossible, but it is a little painful, not painful, delaying. So recently, originally we all learned to transfer files with SCP command, but recently there was a little bit of simplification. We were able to just use buttons with click and drag and drop. For NERSC, they will not allow this stuff. We will need to do SCP. And it is a price we pay for high power of this stuff. The commands are similar but not identical, so it will be a little delay. So by the time we finish these two things, probably it will be, everyone will be tired and we will need to update and relax. But next step that I want to start today, if time allows, is to go towards the concept of thermalization. And nice seeing you this camera. So heating and molecular dynamics. So those things are highly efficient. They help to model like docking, chemical reactions, but they are more expensive than stuff that we did before. And we can start doing them on photon, but for sure they need to be practiced on NERSC. And now it is only an outline. We will go into details. But the main thing, one, and I will repeat it maybe 10 times during the main course, molecular dynamics cannot be run without heating. And heating and molecular dynamics are two different types of job. So before one will be able to run molecular dynamics, one needs to start heating. And yes.
So heating means temperature dependent.
Yes, it is thermalization. It is assigning velocities to each atom.
Yeah, so more interactions and more complicated.
So it's not complicated for humans, but it is much more time demanding. And maybe if you can run at least one heating job on photon and on NERSC, it will be a good preparation for our next unit.
So that means that the processes or the calculations we're using other softwares could be achieved at 0 Kelvin, for example?
Molecular dynamics.
Time independent.
Molecular dynamics at 0 Kelvin doesn't make sense.
Okay, so is it
as soon as something is moving, temperature is bigger than 0.
Is it when we started talking about shooting the equation time dependent and time independent using or so depending on solving the equation dependence shooting the equation?
Thank you. Your question is correct. Okay. But the answer is more detailed.
Okay.
And
I didn't get to the announced course.
So Lina did ask more details, more clarification about molecular dynamics. And her question was, does it deal with time-dependent Schrodinger equation because time is involved? And the answer is more no than yes, because before we start these things, and we will start them at the end of today's meeting, and then the next lab will be dedicated to them. Before this meeting, we have forgotten everything we did in our first months of the lectures, when we were considering nuclear and periodic degrees of freedom. As soon as we practice molecular dynamics, we allow nuclei to move. So it will be Schrodinger equation coupled to Newton equation of motion for ions. Make sense?
Yeah.
And if we launch heating and problem molecular dynamics jobs today, then they will be done by next week, and we will be able to analyze them. And I realize that these ambitious plans are wishful, but maybe hard to complete. But it's my plan. And then VMD is the best tool to analyze results of molecular dynamics. So if you experience difficulties in installing VMD, let me know ahead, so we can solve it cooperatively before next lab. I have some backup solutions, but they are not evident. There is nothing better than VMD. So please log into your start the mobile external, log into Photon servers, and for the first, hopefully, 45 minutes, and practically it may take even up to the whole meeting, I am going to obtain the following 4 figures. So I will just speak about them and to entertain you and satisfy your curiosity, but please better only if you already logged in. So life is not a village. I'm trying to avoid writing equations and discussing. Some of you have, well, all of you have submitted conductors. Providing answer to the last 2 questions with different level of utilization. The second last question about equations for transition dipole was intention. It was a path to today's lab. So the figures, 4 figures that I'm going to show, they illustrate ability of a molecule to absorb light at certain wavelengths or at certain transition energy. And if you do wet chemistry synthesis and characterization, you may have seen this spectrophotometers or read about them in articles. Some labs involved, and some of you are doing your practical research. So the question is to screen all possible transition energies or all possible excitation energies and see at which transition energy system absorbs better, at which it absorbs worse. So the energies at which these peaks happen, they are equal to difference between orbitals, orbital energy. The lowest transition is the energy difference between coma and coma that you were finding in the labs and homeworks. And amount of these transitions is much bigger than the amount of orbitals, because it is basically number of orbitals squared, number of occupied times number of unoccupied. Between each orbitals in those pairs, transitions are possible, but some of them are efficient Some of them not. So the height of the peak is different. A lot of experimental community prefer to do this plot in the wavelength series. So if you notice, in previous plot, we start x-axis from 0 in the order of increase. So energy increases, frequency increases. And wavelengths are inverse units. They are energy divided or constant divided by energy. Okay? So infinite large wavelengths means zero energy. So one should going backwards on this nanometer axis is increased energy. So this is the first peak. And then one goes like from red to blue, and there are additional peaks of different height. I do have intentions to discuss equations for this stuff, and it is not complicated, but we better focus on practical side. And same peaks, same spectra for the same system can be, here I'm showing them computed on photon and on NERSC. And this one is also as function of energy, just a little narrower window. So first peak is around 3.2, 3.3, right? And then there are some peaks of different frequency. And one can also represent it in as function of nanometers. So I'm going to show practical steps how to arrive to these figures. And if you are part of the homework for the next weekend and beginning of the next week until Wednesday to compute the same style of figures based on the models, the same models you practice now. Some of you did receive comments from me about your homeworks, even if homeworks were getting high grades. There were some constructive criticism. So while going towards the next homework, if you want, again, my main goal is to check that you know that you will be fluent in practical steps. But if you care about the scientific correctness of the results, you may do additional steps towards improving of the models. For example, in some of the homeworks, I noticed that elements were swapped. So while building pod car, one swapped silicon and hydrogen, and then it was WASP does not forgive some questions, such errors. So, for example, in silicon nanowire, if you swap silicons and hydrogens, then the backbone in the center will be hydrogens, which themselves are not happy to bond to each other, and the weaknesses on the side were silicons, which were not compensated by additional hydrogens. So such system will predominantly have no gap, which differs from external. It will show metallic behavior while silicon is expected to be semiconductor. So to the next homework, you can revisit and improve. Another thing, I was skipping the procedure of optimization for the models because I didn't want Steven to get angry at us for overusing the formula. And the same for molecular dynamics. So for educational purposes, we can run a little bit, but for productive, let's use most. So after the model is built, one can directly go into electronic structure. But in between this, one can run a job for optimization. And if atoms are coming into optimal configurations, the band gap and other observables become more realistic. So if you have energy and steam, you also can try to re-optimize your models towards that forward. Again, it is not the main task. I will be checking primarily your ability to generate absorption stuff, but for model training you can practice. So let me share screen, and if I will try to practice same style as before, showing something and circulating the sheets and asking those online to share screen. But if I forget to do something, do not hesitate to attract my attention. I can get too excited with typing commands, so please help me to stop focusing on the computer rather than people. Yeah. As we go through practical side, I'll refer to the slides and give some additional explanations, but right now let's go directly to the practical aspect. So I did log into Photon and created a directory for lab number 9 and subdirectory ABS for absorption. I'm going to repeat all steps so that you will see that nothing is set up. So absorption B. So in this directory, I do need a couple of files from my previous run. So from LAB9, I do need the states. So it is the directory where I was doing the titanium dioxide nanowire, where I was doing the density of states and the orbitals. So although I will not directly use it, but I can copy input files, postcard, postcard. So the computation of absorption structure does need information about orbitals, as you were writing in your homework assignment, right? So one needs transition dipole, one needs oscillator strength, which depends on transition dipole. And I see that these words may scare some of you or bring you out of the comfort zone. So show me signs if words transition dipole and oscillator strengths are okay or not okay. Okay, more or less. Lola, is it okay, not okay, or more or less?
I didn't hear what you said about transition dipole.
Does the word transition dipole, so do you feel comfortable with this word? Do you know what it is?
No.
Okay, so at least in the lecture number 16, when we were considering observables, we were looking for the matrix, transitional matrix element. We were looking on the interaction between light and matter, and we were looking on how the system comes from ground to excited state. And in order to evaluate intensity, we were putting the transition dipole in between them, right? So it is what was what you were invited to write in the last homework. So this transition dipole does depend on orbitals, right? It includes orbitals. So orbitals are saved in the file wavecraft. And we will use them not in the nice graphic form as you were showing in your homework, but it will be used in the computer style file. Do not try to look inside this file. It will bring a lot of garbage to your screen. It is not readable by human. But we need to read this file and practice transition dipole calculation. Let me check. Maybe no, I'm skipping this equation. Maybe I'll write it today, but I want to be quick in practical things. So also need states. So practical steps. First, I copy states into file under different name, energy and population. Then I count number of lines there. Then, if I do not trust my memory, I look at my cheat sheet. So here is the code that converts the list of orbitals and wavecar file into information needed for absorption spectrum. If I hit enter right now, it will bring me an error because there is no input file. So before I practice this code, I need to create a third file, which with name input overlap. So the total number of orbitals here, they go from 1 to 39 for this specific system. So I create file VI input overlap. First line 1, second line number of orbitals, third line 1, which means nothing. It's just I was lazy to change the code. It was used before. So file input overlap is here, and after that, I execute this binary oscillator strength dipole version 3, and it starts bringing some information. And upon completion, it reports that things are done. So ls-t. There is a new file called oscillator strengths, and it is about, for this system, it is about 20 kilobytes, so 20 times bigger than the state. So please try to follow these lines, and I will circle around and then ask you to share screens one by one so that we all are on the same page. So we co-host. Host. And him I can bring to the file input overlap, and the command is this one: binary oscillator dipole.
After
So I created the device, but
Just
confused.
which one? Just
Yeah,
try.
what?
I tried to copy the
Oh, MIT homework. I don't know this month. I think it's one RH. I haven't finished it yet, but I'm very to like boards. Reading through it, and then I just over it. Yeah. I haven't really given it a shot yet, so that's for sure. We're talking about that. But Oh, well, we'll see. I think that one should just be. Think. You just know the same equation. All zeros. K at the corner. I have to figure out what K is, but it's just be one K and the corner. That's just reading it real quick. That's my intuition, but like to be wrong.
Really just these two commands, nothing else. Let's start sharing screen. Kay, would you like to be first? I don't hear.
There's some problem with my microphone. Just a minute. Professor, are you able to see my screen?
Okay, yes, I see. I see. Can you please type PWD?
Okay. PWD. Right?
Okay. Can you type ls?
Enter.
Enter.
I already copied, but then I
I
missed.
see. What is your states file? Please copy states file that you used for the density of states.
Oh no no no.
Do you have in a different directory?
No, it's the
Maybe
same.
it's in different in LAB9 or
Okay, in a LAB9. Oh God. LAB9, I guess. So,
more space states. States. Enter. Space.
Okay.
CP.
CP.
Space. States.
States.
Space.
Hmm.
Lowercase energy.
Lowercase energy.
Energy. No, not lesser. Just energy. Type the word energy. Energy. Underscore POP.
Underscore POP.
Lowercase POP.
Okay, okay, okay. POP.
Enter. Okay. WC space
States.
energy underscore POP.
Okay. Energy. Okay. Enter.
Enter. Okay. VI space lowercase input underscore overlap. Input underscore overlap.
Lab.
Enter.
Then one
Letter I.
I.
1.
39,
Enter. Enter.
39,
39.
1.
Enter. 1. Enter. Escape colon WQ.
Yep.
Enter.
Yes.
Tilde. Tilde.
Yeah. Just
The
like
wavy line.
yes.
Slash bin. BIN. Slash uppercase OS
OS.
underscore dipole lowercase DIPOLE underscore V3
V3.
lowercase v and number 3 version 3.
Okay. Done.
Enter.
No. Okay.
Okay. Arrow up. Delete couple of just delete couple of symbols at the end. Backspace, backspace. Hit tab button. Hit tab button. Tabular. Tab, yes. Now type letter V, lowercase.
D.
V, V,
V.
V. And hit tabular once again. Enter.
Okay.
Now type ls minus ot, ls space minus ot. You see there is a file os underscore strengths.
Yes.
And you can type more space os underscore strengths.
This one? This command?
OS uppercase OS, no, O uppercase OS underscore strengths. Uppercase strengths.
Upper.
Third file in the list. You see?
SCR.
And hit tab, it will automatically continue. Strength.
Oh no. Tab. Yes.
NGTH.
Mhm.
Enter. Okay, you're good. You can stop.
Just one question here. Let's go. So this OS strength, it's
I will explain what it means. Let me check that everyone obtains it, and then we'll discuss it.
okay. OS strength, then energy pop. I don't know what is this. Okay.
I'll give comments what they mean. I'll just rush so that everyone can practically get them. Okay, thank you. Lola, would you like to share screen?
Yeah.
Mhm.
Okay. LS, please type LS, enter. CD, go into the directory where your files are, ABS or ABSB, whatever you decide.
It's empty because I couldn't.
Okay, then we'll populate them. So
I couldn't copy. I don't know. I think I checked LAB9. I don't think it contains what I need.
let's do it together. We'll find it out. If not, we'll just recompute. It's a matter of a minute. So please hit arrow up. Arrow up. Stop. Backspace. Backspace a couple of times. Now hit tabular button. Tab on the left of your keyboard. Up TAB. You see there is a next to the Q.
It's not doing anything.
Okay, then Control C to stop it. Control C or just backspace everything. Type LS space. No, LS space. Do enter. Double dot.
Double what?
Double period. Just
Okay.
repeat the same thing as in the previous line. Period
Okay.
slash period slash LAB7 slash enter. Can you please type PWD? Enter. Okay. Yeah. So let's go to, oh, your LAB7 starts with uppercase. You see some of your labs, some
Yeah.
of the directories start with lowercase, some with uppercase.
So, okay, I need to go back to LAB9. Slash, right?
Yes, and not CD, but CP. You can do every, you're not CP, CP, yeah, now go to the end of the line. And check if states, or you can space period.
Should I write it again?
Can you share with me, can you permit me to type something on your computer?
Okay.
I know you are teaching me how to do it, but I have forgotten. And let me know when it is. When
You can. I've allowed you.
No? Oh, okay. So let's check what is in your Lab 7. There should be state because I see this DOS Fermi file.
Can I check lab 8?
By some reason, maybe.
The states. I mean, yeah, the states.
Oh, it is here. It is here. Good.
Yeah.
We have states. No, not ls. We need to copy. Copy. And we also need the wavecar. And just in case, we can copy postcar. And keep. Just in case. Okay. So I think it would be more helpful if now you type yourself, so you can withdraw privileges from me. And now please start copy CP space states. CP space states space lowercase energy underscore POP underscore POP. Enter. VI space input lowercase input underscore overlap input underscore overlap. Enter. First letter I to start inserting. 1, enter. 39, enter. 1, enter. And now escape column WQ. Okay. And now tilde, the wavy line, slash bin, binary, slash OS.
Sorry?
Uppercase letter O, uppercase letter S. OS underscore dipole, DIPOLE underscore letter V and number 3.
You said D as in dog?
No, V like Victor. Lowercase. Enter. Let's arrow up.
The dipole should be without the E.
Maybe let's do uppercase. Upper arrow up. Erase. Yeah, try. Yeah. Oh, okay. Now do ls space minus LT. Enter. So you see the third file in the list is OS underscore strings. Yes. Can you please type more space and then name of this file? Enter. Okay, you're good. You can stop sharing.
Okay, thank you.
Thank you. And Sarah, would you like to share your screen?
Yeah. Dr. Green, first I have a question.
Which outcar file we should copy? The one in the LAB9, which doesn't have orbitals, or the one from LAB9B, which has the orbitals?
The outcar that has orbitals.
Okay. So for me, I face an error.
Not a problem. We will fix it. Can you type ls? Enter. ls minus lt. ls space minus lt. Enter. Okay. More space energy pop. Space energy underscore pop. Enter. Space. Okay. vi space input underscore overlap. Overlap. Enter. Letter I. Number 1. Enter. 39. Enter. Number 1. Enter. Escape. WQ. Enter. Arrow up. Arrow up. Arrow up. Arrow up. Arrow up. Enter.
Oh.
ls minus lt. ls space minus lt. You see the file number 3 is os underscore strengths.
Yeah.
And type more space os underscore strengths. Enter. So you're good. You can stop sharing.
Thank you.
So you have received this.
Professor.
Yes.
When I copy the outcar file, I copied from the LAB9, and that has no orbitals. So I need to copy that one from the previous lab, right?
Well, as long as you do have states, it doesn't matter.
Okay, then it's fine.
We are just copying it as a backup. Cert use one. As a little relaxation, I will speak about this file. So you probably see about 9 columns, right, in the file, and we didn't practice votes on who present what during presentations, but the one who will select UVS spectra is expected not only to share practical things, but also explain what the data means. So here are verbal explanation, and I'll probably write one repeat equation from the lecture 16 and from your homework. So columns 1, 2, 3, 4, 5, 6, 7, 8, 9. So the first and second are initial and final orbitals. So this orbitals between which transition is happening. Columns 5 and 6. So column 5 is associated with column 1. So it is amount of electrons in orbital that is in column 1. 2 electrons. Column 6 is amount of electrons in the orbital listed in the column 2. So 0. We look for transition from orbital with 2 electrons to orbital with 0 electrons. Right? Now, the column number 4 is, if you call this one as I, this one as J, then we can define energy of empty orbital, energy of filled orbital, and this energy difference will be stored in the column number 4. Transition energy that we list along x-axis when we do spectrum, right? The third column is most important, is so-called oscillator strength for pair of orbitals Fij, and it corresponds to the height of the peak, right? The bigger the number in column 3, the higher the peak. And it doesn't need to be tall. Some transitions are, if the peak is high, we tell that it is a bright transition. If it is close to 0, we tell that it is dark transition. Yes?
So does that mean it's more likely to absorb
Exactly.
the light the higher the peak is?
Yes. So, and the remaining peaks, remaining columns 7, 8, and 9 are projections of transition dipole. Yes.
If like
There are no stupid questions. There are stupid answers.
if the oscillator strength is it like a linear relationship? So like if one has a strength of 2, another has a strength of 4, is the one that with strength 4 twice as likely to absorb a photon than the one that was 2?
Mm-hmm. And the data in columns 7, 8, and 9, they are often not needed. They are intermediate data which help to compute oscillator strengths. Technically, the dipole, which sometimes called with letter D or sometimes called with letter mu, J, mu, J, is integral of phi I r phi j dr, right? And since it is a matrix element of a vector, it has 3 components, x, y, and z, and they're stored here. And oscillator strength is approximately equal to j absolute value squared times some constants. So if we look for properties of materials that are homogeneously spread in like solution, then there is an orientation average, and we need average oscillator strength. But if you are if you have some anisotropic material, if you have crystal where absorption along one axis and another is not equal, then one may come back to this data. So it's for 99.9 applications, it is not needed, but just in case we keep them here. And basically, well, I already drew it, but let me offer the question that the one who will select the subject for presentation may offer it. So absorption at frequency, certain frequency, is computed in a similar way as we do density of states. So oscillator strength times delta function, which may have we may assign it artificial width, and here we have this frequency minus energy difference J minus E I. Okay, the oscillator strength itself is equal some factor times it's C times D x ij squared plus D y AJ, G, AJ, and the D, J is integral I J. Okay. So it's just if you have curiosity what we are doing. So we are putting this stuff. Okay. Yeah. So height corresponds to Fig, and the position corresponds to energy J minus energy I. Yes.
Just before going to the next step, so the three numbers that we put into the input overlap file. So we how we choose these numbers?
First orbital, last orbital, and the number 3 is always 1. So
it was for our model 1, the first number.
First orbital, 39 was the last orbital, and 1 is always 1. Okay. For checking. So spectrum improved version 3. Tilde bin spectrum improved version 3. And it will not work right away. You need some information. So same. So when we were practicing visualization of density of states, we converted discrete list of energies into continuous distribution. Now we do have more or less strengths. So you have discrete list of transitions. So this is transition energy, this is height. So we need to convert discrete list of transitions into continuous spectrum. The procedure looks the same, code is basically the same, and the way how we operate is very similar. So we need to type some input parameters, and one of them is just a summary of how many lines are in the oscillator strength file, right? So in order to count lines, I type WC OS strength. So 224 lines. And I think there also it will ask the number of home. And if I have forgotten it, I can scroll through energy pop and see that last occupied is 32. And also some of your questions about last email included request to specify the window, the range of energies in which we plot density of state. So in a similar way, when we convert discrete set of optical transitions into spectrum, we need to specify a window, right? So if you know nothing, if you shoot blind, you can specify from 0 to 10, but it is a little too ambitious. It's just general because there are no absorption below 0, and we don't carry an absorption above 10. But one can also estimate this range by looking on the list of orbitals. So lowest transition will be at the difference of these energies. So minus 3.5 minus subtract -7, so about 3. And then maybe we need another 3 electron volts above. So I can go up to 6, and I can start either at 0 or I can start at from 3 to 6. So it doesn't matter now. Okay, so I think it's enough information. So I'm typing this comment, and last time I have forgotten to share comments in the chat line. Chat line, come on. Everyone, please. So number of transitions, 224. Energy difference. And do not put 0. It should be like 0.1 because for nanometers it divides by difference of energy, and we do not want to divide by 0. So from 0.1 to 10. 0.1, 10. Width of line 0.005. Number of HOMO 32. So after this command LAB9 I am getting a file which is named spectrum. If and you see that it is about 10 times larger than oscillator strength because it has more points. If I hate the plot, I can just download this file spectrum and plot it with Origin or Microsoft Excel. But I'm going to convert it into graphical format with GNU plot in the same style as we did for density of states. I'll probably finish because it's just a couple of lines and then I might be sorry. So GNU. Oh, let maybe if some of you are.
So what's the previous?
Yes, absolutely. I can even share this one. Copy. Chat line. Paste. Yeah, thank you. So meters. So I'm going to run a GNU plot command with this couple of scripts, and you see that it just plots file spectrum with lines 2 and 3 and with lines 1 and 3. So line 3 is intensity of transition, line 2 is transition energy, or line 3 is intensity of transition, line 1 is nanometers, not line, all of them. So I'm typing GNU plot this one, and then GNU plot this one. Share them just in case also in the chat line. And then I can LS-LT. So I'm getting two files, spe.ps and sp nanometers.ps. And I convert them ps to pdf wr spe underscore nanometers. Copy. Chat line. Paste. Now I do ls minus t. And it has this PDF files, which I can go into this directory, absb, and there is file spe.pdf. So it shows first transition at 3.3 electron volts. And if I look here once again into more strengths, look at the first line. So transitions from HOMO to LUMO plus 1, 32 to 33, at 3.3 electron volts with intensity that is bigger than anything else. So the lowest transition is the strongest one. Well, it is not the lowest. The HOMO to LUMO is, I do not see it in this list. It's somewhere lower. Okay. I'm going to make a circle and make sure that you are comfortable in reproducing this thing.
It's on the vertical axis. So how would it feel like wanting a highlighted to
There is an effort to normalize it so that we will, otherwise, if you take bigger system, it lower and lower,
that's all I
which is discrete. Okay, would you like to share your screen?
Oh, this will stop others. What happened? Continue.
Okay.
So I did this.
And just try to I think the files are ready. Try to download them and show that you can see them.
And what's the command? I forgot.
Let's just move your mouse slowly to the left.
There?
Mouse slowly to the left. Can you move?
This one, right? There?
Yes, and there is a green symbol. Yes, double click.
Yeah.
Double click.
Yeah, I already clicked. It's loading.
Mhm. If it does not follow your command, okay. Yeah, type the reconnect SSH browser.
Yes.
Okay, and now double click on this greenish. Now
Then
scroll up, double click on green symbol. Now scroll down, yeah, CHEM, yes, and then for year 20, yes, yes, the
LAB9.
whatever you get, okay, description, and then bring this PDF files.
This one?
Yeah, start from this one and then, yeah, and this one as well. Please download. Can you open them?
Yes. I think it's automatically open, but oh, there are lots of files. I think this too. No, not this. This one from homework. Oh, okay. This one and this one.
Okay, yeah, excellent, excellent.
Done?
Yes, yeah,
Okay.
super. Thank
Stop
you.
sharing.
You can stop sharing, yes. Sarah, would you like to share screen?
Yes. This is
Okay, yeah, it's perfect. I see it. Excellent. it was really quick. Yes. Thank you. You can stop sharing.
Sure.
Lola, would you like to share screen?
Yes. PDF.
Okay. Okay, yeah. And yeah, very good. Thank you.
Okay.
You can stop sharing screen.
All right.
So we have completed minimal part of our plan. So we did this. We're done with UV visible absorption spectrum more important. And I think now it will be reasonable to focus on how to do it first, how to do file transfer. So in case you care only about the grade in the course, it will be auxiliary. But if you plan to do research, maybe it's more important than the rest of the things. So if you are taking records, if you have some additional file where you're taking electronic records, you can, just in case, record the directory where you did this little exercise. Just in case if I forget. Now, I am going just CD with no arguments. So be careful. This command will bring me to the root, not to the root, but to the user directory, and it may take then few additional time to come back to this directory. PWD. And now from here,